All right, guys, we're in the final stretch of electron configuration and also quantum chemistry chapter in general, chapter 6. And so that's great. We're just going to do a bunch of practice problems pretty much now with a little bit of nuances, a little new concepts, but mostly practice. Okay, so first two questions. What are the orbital diagrams and electron configurations for sodium and selenium? So we're going to use the shape of the periodic table to help us out. So here's the periodic table, right? And so we're going to go hydrogen to helium. We're looking for sodium. Sodium's right here, 11. So we're going to go 1s2, 2s2, 2p6 brings us to neon, and 3p1. Okay, that gives us 3s1. This is the s orbitals. Okay, so again, 1s2 helium, 2s2, 2p6, 3s1. Okay, and if we drew out the orbital diagram, we'd have each of the orbitals would have 2 electrons, spin up, spin down, right? The p orbitals can have 6, the s orbitals hold 2. By the way, right, I mean, this makes sense. That's why the p block here, what we call the p block elements, that's 6 wide. From boron to neon, that's 6 wide. Okay, from thallium to radon, that's 6 wide. That's the p block. From lithium to beryllium, that's 2 wide. That's the s orbitals. Okay, because there's only 1 s orbital. There's 5 d orbitals. That's why from titanium to zinc, okay, it's 10 wide, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Scandium to zinc. Forgot scandium. Scandium to zinc. Okay. All right. Selenium. Let's do selenium. 1s2, 2s2, 2p6 gets us to neon. 3s2 gets us to magnesium. 3p6 gets us to argon. 4s2 gets us to calcium. 3d10 gets us to zinc, and we're doing selenium here. So 4p, 1, 2, 3, 4, 4p4, 4p4. We pair all those electrons up and down till we get to the last orbital. Then we have to follow Hund's rule. So here I went down, 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 seats on the bus, separate orbitals, and then one up is the 4th one. Okay. So you know, this can be very tedious, especially for the elements with a lot of electrons. And so what we like to do instead is what's called abbreviated electron configuration, where we use brackets with the nearest noble gas. So you could write phosphorus like this, but those first 8 electrons are really the same as neon. You're just filling up neon. They're not valence electrons. And so we just put bracket neon and then add the valence electrons, 3s2, 3p3. So you could write phosphorus this way, the full notation, or equally acceptable would be to write bracket neon and then a lot shorter. Potassium's another example. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Up to 3p6, that brought you to argon. That's a noble gas. Put bracket argon and just put 4s1. Saves you a whole lot of time, okay? A whole lot of writing. So that's what we'll do. Of course, the exams are multiple choice, so you're not really doing a lot of writing anyway. Some practice, okay? Electron configuration for lithium. And so that's going to be bracket helium if we want to do that, 2s1. Why? Got to helium, that's the nearest noble gas, and then lithium, 2s1. That's all that was there left. Write the electron configuration for aluminum now, 3+. So we're going to have to do aluminum and then remove 3 electrons to make it 3+, right? Because electrons are negatively charged, we're going to have to remove 3 to make a 3 positive charge. So let's get to aluminum. Aluminum's right there. Well, the nearest noble gas is neon. And it looks like I'm going to be bracket neon 3s2, 3p1. So let me write that down first. So I would be bracket neon 3s2, 3p1. Okay, that's for neutral aluminum. So that would be the answer for neutral aluminum, but it's not asking us for neutral aluminum. It's asking us for aluminum 3+. So we got to remove 2 electrons, 1 electron, 3 electrons, right? Remove these 3. So it's just going to be bracket neon, okay? Write the electron configuration for cadmium. All right, so you go to the periodic table, 1s2, 2s2, 2p6, 3s2, 3p6 goes to argon. Okay, we could keep on doing this, blah, 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 but remember, use the noble gas configuration. All right, cadmium. Just look at cadmium. It's number 48. Okay, nearest noble gas that's before it, krypton. Bracket krypton, it's going to be bracket krypton, 5s2, 4d10. 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's how we do that. Things that are isoelectronic, atoms or ions that are isoelectronic. Iso means same. So same electron configuration. That's what it means. So for example, if you do krypton, selenium 2-, selenium dianion, and strontium cation, those all have 36 electrons. They all have bracket krypton electron configurations. Okay? Same electron configurations, isoelectronic, same number of electrons. Some random review questions that related to quantum chemistry topics, not totally random. How are frequency and wavelength of light related? Ooh, great question. Got to know this. The lower the frequency, the smaller the wavelength. You can pause this video and try to answer this if you want. The wavelength and frequency are equal. The larger the wavelength, the higher the frequency. The higher the frequency, the smaller the wavelength. Okay? The answer is the higher the frequency, the smaller the wavelength, right? Higher frequency, that means smaller wavelength. That means more energy, okay? That means more red. That means more blue, sorry, on the color spectrum. It's going, okay, more energy. All right, another question. Which of the following are true? Again, you can pause this video and try to figure this out if you want to. But let's just go through these. Electrons occupy orbits. No, and orbitals, right? Schrodinger equation is all about orbitals. Are not fixed paths of orbits. It's not like the solar system. Up to 2 electrons cannot occupy one orbital. Yeah, true. Spin up, spin down. Orbitals are probability maps indicating where electrons are located. Yes, that's what we're doing. Heisenberg's uncertainty principle tells us we can't know exactly where electrons are, but we're going to use probability maps to give us a general idea. Orbitals have shapes. Yeah, that's true. Orbitals have energy levels. That's also true. N equals 0, N equals 1. Those are the periods on the periodic table. Orbitals have spins. Orbitals themselves don't have spins. Electrons have spins, right? Plus 1/2, minus 1/2. Orbitals have beautiful colors. No, they don't have colors. They're tiny. Our eyes can't see anything that small. Color doesn't even make sense at that small, okay? Color, what is color? Color has to do with our eyes, okay? Or you could talk about the color of other animals, which is very fascinating, by the way. You know, birds can see in the ultraviolet, for example. Don't get me started getting distracted by, you know, wonderful concepts in science. Okay, so 2 through 5 were true. Next review question. Which of the following elements has the following electron configuration? So, I mean, basically for this one, again, you can pause the video if you like. I would just add up the total amount of electrons. So 2 plus 2 plus 6 plus 2 plus 5. That's going to get us to, what is that, 17? And I believe that's going to be chlorine. And yep, that's chlorine. Just looked at the periodic table to confirm that's chlorine. All right, so let's stop it here for that video. And we're almost done here, guys, on this chapter.